Hello maths fans, Dr Tom Crawford here at the University of Oxford, continuing the Oxford Linear Algebra series in collaboration with ProPrep. Today we're looking at determinants once again, but this time in combination with elementary row operations or EROs. The main idea is to be able to use EROs to simplify our starting matrix into something where it is much easier to calculate the determinant than if we were to expand in the rows or columns. So what we need to know is how the EROs modify the determinant. In part 1, we saw how to calculate determinants explicitly for 2x2 and 3x3 matrices, and we also explored some of the properties of the determinant function. These are going to be really important in what we're doing in this video, so here's a quick reminder. The determinant function is a function d which maps from the n by n matrices to the real numbers such that it has the following properties. So the first one is if we swap two rows in our matrix, then d goes to minus d. So you introduce a negative sign if you swap two rows. The second property is that multiplying a row by a scalar, let's call it lambda, causes d to go to lambda times the original determinant. And finally, if we have any repeated rows, then d is equal to 0. These three properties were in fact used to define the determinant, and I mentioned in the first video that they can be used to show that the determinant is unique, and therefore the formula that we use to calculate 2x2 and 3x3 determinants is in fact the only such way to get the determinant function. Now, if we think back to elementary row operations, which were also covered in a previous video in the Oxford Linear Algebra series, we have three different types. So the first type, we'll call it type 1 ERO, is that you are able to swap two rows in your matrix. The second type was that you can multiply a row by a scalar. And the third type of ERO was you can add a multiple of one row to another row. Now, as I've mentioned, we want to do elementary row operations to our starting matrix that we're trying to find the determinant of. And so as we do these operations, we need to keep track of how the determinant is modified. Because if we're changing the matrix, we need to make sure we change the determinant in the same way so we know how to get back the original determinant that we wanted. Now the first one, swapping two rows, well, that's exactly defined as a property of the determinant function. So whenever we swap two rows, we just remember that the determinant will swap signs. So every time we do this, we get a minus and then become a plus and then a minus and a plus. So however many rows we swap, we just remember to multiply by -1 that same number of times. Similarly, if we do the type 2 ERO, we multiply a row by a scalar, then our determinant is multiplied by the same scalar. So we can keep track of how that also modifies the determinant we're trying to get for our original matrix. However, this third one, where we add a multiple of a row to another, you'll notice this isn't explicitly mentioned in the properties we used to define the determinant. So this third type 3 elementary row operation, to figure out how this affects the determinant, we're going to have to think a little more and we're going to have to do some more work. Don't worry if you aren't familiar with elementary row operations or you missed the first video in the Oxford Linear Algebra series, because ProPrep has got you covered. ProPrep is an online resource that provides customized tutorials for students looking to improve their skills in STEM-based subjects. And if you sign up using the link in the video description, you'll receive a 30-day free trial, which will give you full access to all of the video tutorials, all of the video exercises, and even video solutions. They cover almost every mathematical topic you can think of, and of course that does include elementary row operations. One of the key concepts of elementary row operations is that the matrix you get when you apply an ERO to your starting matrix can actually be obtained by pre-multiplying the starting matrix by something called an elementary matrix. Now this is perhaps easiest to see with an example. If I have a matrix A and then I apply the type 1 elementary row operation, I swap two rows, then this matrix A goes to this matrix, let's call it A prime, because the original A has been changed in some way. Now the same matrix A prime can be obtained by taking your matrix, starting matrix A, and pre-multiplying by an elementary matrix, which I'm going to call E12, for example, showing or representing that this swaps the rows 1 and 2. So you can use matrix multiplication to get the same outcome as you would if you were to just swap two rows. And this matrix, in this instance E12, is in fact just the identity with rows 1 and 2 swapped. So if we take it to be a 3 by 3 matrix, then we would have 1, 0, 0, 0, 1, 0 on top, 0, 0, 1. So the ERO that you want to do to your matrix A, to get the elementary matrix, you simply apply the same elementary row operation to the identity, and then you pre-multiply by that matrix. So when you're swapping rows, it's just a case of swapping the rows in the identity. When you're multiplying a row by a scalar, so let's call this E lambda 2, for example, so signifying we want to multiply the second row by lambda, then we do the same to the identity. So it's 1, 0, 0, 0, lambda 0, 0, 0, 1. And for the third one, the more complicated type 3 ERO, we just add a multiple of a row to another. We do the same thing to the identity. So let's suppose we want to do the first row plus k lots of the second row. So let's call it E1 plus k2 to really spell out what's happening. So we just do the identity. So rows 2 and 3 don't change, but we're going to add k lots of row 2 to row 1. So the first entry here is 1, the second entry is k, and the third entry is 0. Now I do advise that you check for yourself that pre-multiplying a 3 by 3 matrix A by any of these three elementary matrices will do exactly what we are hoping it would do were we to apply the appropriate ERO. Now it is worth pointing out that whilst I have given some explicit examples of a 3 by 3 elementary matrix, the exact same process will work for an n by n elementary matrix. So again, you just take the n by n identity matrix, apply whatever ERO you want to do to the identity, and then pre-multiply your original matrix by that elementary matrix. So now that we know the application of any of our type 1, type 2, or type 3 elementary row operations can be represented, or in fact is the same as pre-multiplying by one of these elementary matrices, we can in fact say that the determinant of our new matrix, determinant of A prime, the matrix we get after applying an ERO, is equal to the determinant of our elementary matrix times A. Because we've seen that A prime is equal to EA, where E varies depending on the type of ERO that has been applied. Now, the determinant function is in fact multiplicative. And what this means is that when you have the determinant of a product, it's equal to the product of those determinants. Now, this property can be proved using the three properties that the determinant function was defined from, but that is beyond the scope of what I want to cover in this video, so I will leave that as an exercise for the viewer. Now, using this property, therefore, we can say our determinant A will be modified by whatever the determinant of E is, where E is one of our EROs. So in order to know how an elementary row operation affects the determinant, we actually just need to know what is the determinant of our three types of elementary row operation. Now, fortunately, for the first two types of elementary row operation, we in fact know exactly how the determinant is modified because that was how we defined the determinant function. So the elementary matrices have had these first two operations applied to them, and the starting matrix was the identity. Whatever the size of the identity matrix, the determinant is always equal to 1. So every time you swap a row in the identity, we know from the properties by which the determinant function was defined, we introduce a -1 factor. So every time we swap a row, for example here we've swapped a single pair, that will introduce a factor of -1. So whenever we swap two rows, we can say for a type 1 ERO, the determinant is just simply -1. We've swapped a pair of rows, and we know for any determinant function that introduces a minus to the original determinant. The original determinant of the identity is 1. Similarly, for a type 2 ERO, where we multiply a row by a scalar, again, the properties of the determinant say this is equivalent to multiplying the original determinant by that same scalar. We started with the identity, so the original determinant was 1. We multiply a row by lambda, the determinant therefore becomes lambda. So here, the determinant is equal to lambda. Now for type 3, again, we've got to think a little more. Now when we add a multiple of a row in the identity to another row in the identity, we are in fact going to end up with something quite specific. So this again is an example for a 3 by 3, but what you can see is we added a multiple of row 2 to row 1, and so that introduces this non-zero element in the top half of the matrix. We in fact say this would be an upper triangular matrix because it has 0 entries below the main diagonal. Now, even if I had added, let's say, a multiple of row 1 to row 3, for example, we would get an entry in the bottom half of the matrix, but the top half would be full of zeros. And you can think about this a little bit for yourselves, and I encourage you to do so. But no matter what multiple of whatever row we add in the identity, we're adding a multiple of one row of the identity to some other row in the identity, we can only end up with one other non-zero entry away from the diagonal. And as there's only one other, it has to be either below or above the diagonal. So no matter what we do for this type 3 ERO to the identity, we end up with either an upper triangular matrix where the bottom half is all zeros, So this would be upper triangular. Or we could end up with a lower triangular where the upper half is all 0. Now, it doesn't actually matter which one we end up with, because in the case of a triangular matrix, whether that's upper or lower, the determinant is always equal to the product of the elements on the diagonal. And it's not too tricky to see why. So if we take a general matrix, and let's suppose I'm going to say we have entries here along the diagonal, up here some entries, and all of this lower half is 0. So this would be an example of an upper triangular. It's the same if it was lower triangular. Now, when I'm calculating the determinant of this matrix, I'm free to choose which row I want to expand in. So we discussed this in part 1 of this video, and you would simply take the bottom row because it only has one entry that isn't 0. So it's 0, 0, 0, 0, 0, so 0 times whatever is still 0, and the only non-zero one is the last column. But we also cross off that last column. So doing our expansion in that bottom row, we're then left with another matrix that's one row and one column smaller, but again it has a single non-zero entry and everything to the left here is 0. So again, we can only expand, the only non-zero thing we get is when we pick that element. So we cross off that. And we're going to continue in the same way. And as we move up the matrix, picking the diagonal element, because it's the only one that isn't 0, through each row as we move upwards, our final determinant is just going to be the product of that diagonal. So what this means in the context of our type 3 elementary matrix, where we have 1s down the main diagonal and some other entry, we don't care where it is. The determinant of this third type of elementary matrix is always going to be 1 because it's a triangular matrix. So for type 3, we can in fact say the determinant of E is always equal to 1. So whilst the type 1 ERO introduces a -1 sign, which again we already knew from the properties of the determinant, the type 2 introduces a lambda factor, which again we did already know from the properties of the determinant. We can now see that the type 3, where we add a multiple of a row to another, that does not change the determinant because the elementary matrix that you pre-multiply by to do this procedure has determinant 1, and we know that the new determinant is just 1 times the old one, so therefore it hasn't changed. So putting this all together, we can conclude the following in terms of how each elementary row operation affects the determinant. If we swap 2 rows, then our determinant D goes to -D. If we multiply a row by lambda, then we know that D goes to lambda D. We multiply by the same factor. And if we add a multiple of a row to another, D actually is unchanged. So it just goes to itself. So what this means is we can now start with a matrix, apply elementary row operations, exactly as outlined here, and record how they modify the determinant. Eventually, we get to a simplified matrix. Hopefully it will be diagonal or upper or lower triangular. Then we can work out the determinant of that very easily, and then we just have to trace our steps back in terms of what we did to the determinant to get the original value. It's actually a lot easier than it sounds, so let's put it into practice and do some calculating. Here's a 4x4 matrix. Now we could expand in the second row because of the 0 to simplify things, and do a row by row expansion to calculate the determinant explicitly. Now, some of you may wish to do this, but bear in mind, you're going to need to calculate 3 different 3x3 determinants, which means a lot of steps and a lot of opportunities to make an algebraic mistake. So instead, what we're going to do is apply a series of elementary row operations to reduce this matrix to something triangular, something simple, where we can read off the determinant immediately. And importantly, we just keep track of which EROs we applied so that we know how the original determinant was modified. So the first thing we're going to do is going to be take the first row and actually multiply by a half. So we'll do row 1 goes to a half row 1, and I'm going to also remember how that affects my determinant. So the original determinant, let's call it D, is going to be multiplied by the same factor. So what we've done is we've started with our determinant D, and we now know it's gone to the value of a half D when doing this particular ERO. So all of these 2's, just rub these out, they're going to disappear, and we're just going to be left with 1, 1, 1, 1. Pretty straightforward so far. Now the next thing we want to do to try and get this into RRE form, or something approaching row reduced echelon form, is to get rid of these first entries in this first column. So what we're going to do is now going to be row 2 minus row 1. We also want to do row 3 minus 2 lots of row 1, and we want to do row 4 minus row 1, because that will give us zeros in these 3 entries. Now, nothing happens to the determinant because of this third rule. I'm adding a multiple of a row to another. I'm adding -1 multiples, -2 multiples, and -1 multiples. So the determinant isn't changed by doing these EROs. So let's do them. So subtract row 1 gives me 0. That 2 is going to become a 1. 3 minus 1 is going to give me 2. 0 minus 1 gives me -1. This is also going to now be -2 lots, so that gives me a 0. Minus 2 from 1. -2 from that gives me a 1. And -2 minus another 2, I think it's going to give me -4. And then row 4 minus row 1, again, that's going to give me a 0. 2 minus that gives me a 1. 1 minus 1 gives me a 0. And this gives me a 1. Okay, now following our rules about EROs, trying to simplify things, we've got a leading 1 here, which is what we want. We've got a 1 here, which is, again, what we want. We don't want these 2. So what we want to do now is, in fact, going to be row 3 plus row 2. So that was kind of the first stage, second stage. And then we're going to do a row 4 minus a row 2. And again, for both of these, we're just adding multiples of another row, so the determinant doesn't change. So if we add on the row above, that becomes 0. We add on the row above, that becomes a 3. We add on the row above, that becomes a -5. Then we are subtracting row 2, so that becomes a 0. We are subtracting that 2, becomes a -2. And then we're subtracting -1, so that's an adding of a 1, which gives me 2. Now, again, we want this 3 to become a 1. So we're actually now going to do row 3 is going to go to a third. Row 3. So our determinant is going to change. So D has now, so a half D has now gone to a third times a half D. And I'm including them together so I can keep track of everything that's happening. Right, so that's going to now become a 1, what we want. And then this is now going to be -5 over 3. Now we just add on 2 lots of row 3 to row 4. So row 4 plus 2 lots of row 3. Again, the determinant doesn't change. And that's going to give me a 0 there, which is what I wanted. And then I've now got 6/3 minus 10/3. So that's -4/3. So that's going to be minus 4 over 3. And now, this is in a significantly reduced form. It's now actually upper triangular. So we can sort of draw this in to explicitly see we have an upper triangular matrix. The determinant you would expand in the fourth row, cross off that, cross off that. So it's minus 4/3 times the 1, times the 1, times the 1. So it is just the product of the diagonals as we saw earlier in the general case of a triangular matrix. So the determinant of this thing that we've ended up with is now just equal to, so we can say the final answer is the det is minus 4/3. But we remember the answer we've got here is equal to 1/3 times 1/2 times the original determinant. So this is equal to d divided by 6. And d, remember, was the determinant of the starting matrix that we wanted. So we multiply both sides by 6. That tells us that d is equal to minus 8. So if any of you have expanded the original matrix row by row or column by column, you should get the determinant to be minus 8, which is the exact same answer we've achieved here by using EROs to simplify things, keeping track of what we've done, and getting a much easier matrix that we can immediately write down the determinant of. If you're still yet to be convinced of the benefits of using EROs to calculate determinants, then I do suggest trying it out on some larger matrices. You can find some exercises on calculating 4x4 and even 5x5 determinants from ProPrep, along with some tutorials and video solutions to really aid your learning. Remember, if you sign up using the link in the video description, you'll get 30 days completely free. Thank you everyone for watching. Please do remember to subscribe if you've enjoyed the video, and I'll see you all soon. Take care.